All right, ladies and gentlemen, we are going to talk about worksheet number 4, problem number 2. You guys ready? You have your stuff handy? All right. So we did problem number 1 yesterday. You guys following along? Guys. All right, we did problem number 1 yesterday. So today we're going to go through problem number 2. So make sure that you follow along and you double check your answers. So for this one, we're given a table that tells us time and position as an object is moving. This is going to be a little bit more complex than what we were looking at yesterday. What we need to do then is make a position versus time graph, velocity versus time graph, motion map, and then solve some problems. So we're going to start working on these. What's a little bit nice about this one is we already have our axes labeled and gridded out and identified as what values go where. So we're going to start with these points. 0, 0 is going to go with the origin. At 1 second, we've traveled 2 meters. 2 seconds, 4 meters. 3 seconds, still 4 meters. So our object has not changed position there. At 4 seconds, the object has traveled 7 meters. At 5 seconds, 10 meters. And then stays at 10 meters for 2 seconds. At 8 seconds, the object is at 5 meters, and then at 9 seconds, back at 0. So I'm just going to go ahead and connect these. It's a little bit easier to see the patterns there. So you should have something that looks a little bit like that, where we've got an object that's traveled in the positive direction, then stopped motion for 2 seconds, and then turned around and traveled in the negative direction. So to make our velocity versus time graph, we have to take a look at this one. And we've already discussed that the slope of a position versus time graph gives us our velocity. So our slope of position versus time equals velocity. So what I'm going to do is calculate my velocity for each of those legs of this trip. There's one there, a horizontal piece, another piece in the positive direction, another horizontal, and then a negative direction. So I know that these flat ones are all going to have a velocity equal to 0 because our object has no displacement, and so it has to have a velocity that's equal to 0. For this first leg, over the passing of 2 seconds of time, we've traveled 4 meters, so 4 meters per 2 seconds. It's going to give us a velocity of 2 meters per second. For the second leg, with a positive direction, the object travels 1, 2, 3, 4, 5, 6 meters in 2 seconds. So that's going to have a velocity of 3 meters per second. And then lastly, we have an object that's traveling in the negative direction. So it's going to have a negative displacement and a negative velocity. So here we're going to take 0, our final position, minus 10, our initial position, divided by 2 seconds. So minus 10 divided by 2 tells us the velocity for this one is minus 5 meters per second. Okay, so over here on our graph, the way that this is going to look is we're going to think about this in terms of chunks of time. So here, the first one is 2 seconds worth of time. So it's between those two marks, and our velocity is plus 2 meters per second. So I'm going to go up to 2 and just draw a straight line there. For the next 1 second of time, my velocity is 0. So my line is going to go right on top of 0 down here. And you don't need to connect those ends, because that would mean that at 2 seconds of time, your object has every velocity between 0 and 2, and that's just not possible. The next one, between 3 seconds and 5 seconds, our object is traveling at 3 meters per second. So between 3 and 5, traveling at 3 meters per second. My line goes up there. Between 5 and 7 seconds, my object is not moving, so 0 meters per second of velocity. So again, we're down there. And then lastly, our object takes 2 seconds to travel in the negative direction at 5 meters per second. So that's going to go way down here, guys. Minus 5 meters per second. How'd you all do?
Great.
Awesome. I appreciate the enthusiasm. All right, our motion map. This is a little bit trickier. We've got 0 meters. You know, there's not 10 here. I'm gonna grab a black pen. I'm going to make these every 2. I'm not sure how you guys did this. Is it? Look at that. You guys are intuiting this, and that's cool. All right, so I'm going to draw all of my dots. T equals 0 is at 0 seconds. T equals 1 is at 2 seconds. 0 seconds, 1 second. 2 seconds, we're at 4. 3 seconds, we're at 4. 4 seconds, we're at 7. 5 at 10. 6 at 10. 7 at 10. 8 at 5. How do you guys feel about drawing motion maps? Does it feel a little bit weird still? It's getting more normal? Well, that's good. I'm going to draw my lines. I'm going to start halfway in between and draw backwards. It's like playing half connect the dots. There we go. There's my motion map. It doesn't ask me to do anything with it, so all I have to do is draw the dots. All right. Determine the displacement from 3 seconds to 5 seconds using the velocity versus time graph. So guys, remember, the way that we can do this is to look at the area under the curve. Right? Because our area is our length times our width. It's the same as doing the displacement is equal to velocity times time. So between 3 to 5 seconds, we are looking at this box here. I'll show up on screen for you guys. There we go. Excuse me. So for that box, we've got a velocity of 3 meters per second and a length of time of 2 seconds. So that's going to be 3 meters per second times 2 seconds equals 6 meters. The other way that we can confirm that is to look at this and say, okay, for every 1 second and 1 meter per second, so each of these little boxes is worth 1 meter, and I've got 6 of them in there. That's another way I can calculate that. And we can confirm that if we look next door here at the position versus time graph. The change in position from 3 to 5 seconds is moving from 4 to 10, so that's 6 meters. So we can use all those ways to confirm that, but our answer should be 6 meters. Next, the displacement from 7 to 9 seconds using the velocity versus time graph. So that's going to be looking at this piece of time right here. Okay, so with that chunk of time, if we are doing the same thing and we are looking for a displacement as velocity times time, which is the same as the area under that curve, our velocity there is minus 5 meters per second, minus 5. Don't forget the minus 5, times 2 seconds gives us minus 10 meters, right? And this asks for displacement. So remember, displacement is a vector and not a scalar, so we have to make sure that we include the sign. We have to give an indication of direction there. So there's all those other ways we can confirm this too. We can look at this and there should be 10 boxes there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could look over here on our position versus time graph, and if we're going from 10 meters to 0 meters, that difference is in fact negative 10 meters. So we confirm that one. Determine the average velocity from 4 to 8 seconds. This is a little bit trickier, guys. So what we're concerned about here is only the difference that happens between 4 and 8 seconds. So if I look at my graph and I find my 4 spot, which is right there, and I find 8 seconds, which is here, now I'm looking at 2 different points. So the way that we can figure this out is our average velocity is going to be the position at 8 minus the position at 4 divided by the time at 8 minus the time at 4. Little subscripts help us remember where things are. Instead of writing the final position and initial position, if you replace those with the times you're looking at, it helps you keep it a little bit straighter. So at 8 seconds, sorry, Yeah, at 8 seconds, my object is at 5 meters. You guys see that from the data table? That's the easiest way to read this because I might be making mistakes over here. So if I go back to the original, I can make sure I don't mess that up. So my position is 5 meters at 8 seconds. And then I'm going to subtract the initial position from that, which is where I am at 4 seconds. At 4 seconds, my position is 7 and the time is 4. Does this make sense? Because I'm going to end up with a negative number up there. Right? Does this look like a negative slope? My black line here? Yeah, it's a negative slope. So we're going to have minus 2 meters over 4 seconds. So I got minus 0.5 meters per second there. Yes, sir.
So I got that right, but I did it differently.
Okay.
So I was just going to ask like if it would work this way all the time.
Yeah.
I just took the velocity like separately at each second. So like from 4 to 5, the velocity was 3 meters per second. From 5 to 6, it was 0. From 6 to 7, it was 0. And
Yeah.
from 7 to 8, it was negative 5. And then I added those all up and divided by 4.
Should work.
Would that work all the time?
It should. Yep. I think this way's faster. Yeah, but it should work. Okay. Lastly, it's determine the average speed. So for speed, we're going to need to do our distance divided by time. So what's the total distance that our object traveled from 4 to 8 seconds? It's the same 2 data points. But what happens here is if we look at what's happening, our object travels 3 meters, then sits still, and then travels another 5 meters. So what's the total distance traveled there? Our total is 8. So we've got 8 meters divided by 4 seconds. This is going to be a very different number, right? This is going to be 2 meters per second. With speed, do we have to report if it's positive or negative? Like, that doesn't mean anything, right? This is a different type of measurement. This is a scalar measurement. We're not worried about negative and what direction they went. All we care about is the total distance that was traveled and the amount of time that it took to get there. So our average speed is going to be 2 meters per second. Am I done?
4 minutes.
I got 4 minutes. Okay. You could do a similar thing with this. You could figure out what the speed was at each point and then average them, and then that should work. For a small problem, it's probably okay. If we had a larger problem, it would be tougher to do that.